Have you ever paused to wonder how the incredibly precise electronics that power our world are actually made to work flawlessly?
Especially when you're dealing with these invisible, super fast signals.
Exactly.
Yeah.
Where even the tiniest mistake can mean, well, total failure.
Yeah.
Today, we're taking you on a deep dive into the very fabric of electronic precision.
It's a realm where, our human senses are completely useless, yet it underpins almost everything we rely on.
Yeah, all our modern tech.
And making sure these elusive signals behave exactly as they should, that takes an astonishing level of meticulous measurement.
Yeah.
Sometimes really ingenious stuff.
Absolutely. And our journey today, it's going to be guided by a fascinating historical
Oh,
document.
yeah. Which one?
The Soviet state standard GOHISTOY 2271.191.
Okay. A GOES standard.
Yeah, and this isn't just some dusty old relic. It's like a foundational guide, almost a Bible for measuring the electrical parameters of microwave electronic devices.
That's right. It basically lays out the rule book for guaranteeing quality, performance in high-frequency engineering back then.
Yeah. So it details the precise methods, the conditions for testing everything.
Pretty much.
Yeah.
From raw power output to the subtle integrity of the signal itself.
So our mission in this deep dive is to really understand the meticulous and sometimes kind of surprising ways engineers made sure these microwave devices performed exactly right.
Across this massive range of frequencies and power levels, too.
Right. You'll get to peek behind the curtain of high-frequency engineering, see the clever methods, the extreme precision needed to keep these critical technologies humming.
We'll show you the real nuts and bolts of how reliability and performance are guaranteed in a field that, can seem almost like magic if you're not familiar with it.
Okay, so let's start by setting the stage then. What exactly are these microwave electronic devices that this standard is talking about?
Well, the standard calls them microwave electronic devices, sometimes abbreviated SWC or AVIN Cyrillic.
Right.
And the category is surprisingly diverse. It covers everything from traditional electrovacuum devices,
Like vacuum tubes, but for microwaves.
kind of, yeah, but also various modern modules, blocks, protective devices, and even cryoelectronic items.
Cryoelectronic, you mean devices that operate at super low temperatures. Why include those?
Exactly. They're in there because microwave signal behavior changes drastically at those extremes. So you need specialized measurement protocols to ensure they work reliably.
Ah, okay. In space, or high-performance labs, maybe.
Precisely. The list also includes thermoelectronically cooled items, things designed to maintain very specific operating temperatures.
That's a really comprehensive list. It shows how widely the standard applied. Now, what about the frequencies? Microwaves mean fast, but how fast are we talking?
Oh, fast is an understatement. These measurements cover an astonishing frequency range,
Yeah.
all the way from zero point zero 0.03 gigahertz, so pretty low microwave, up to an incredible 178.6 gigahertz.
Whoa, 178.6 gigahertz. Just for context,
Yeah.
typical Wi-Fi is like 2.4 or 5 gigahertz.
Right, so this is orders of magnitude beyond that.
It really highlights the sheer versatility and, frankly, the huge engineering challenge of working with these devices.
Absolutely. Operating across such a wide band with such different devices, well, it demands equally versatile and incredibly precise measurement techniques.
And what were the general conditions for these measurements? Were there specific environmental rules?
Yes, quite strict ones, actually.
Mm-hmm.
Unless the specific device's documentation said otherwise, all measurements had to be done under normal climatic conditions.
Standard room temperature and pressure, basically.
Pretty much.
Yeah.
And crucially, the procedures had to match the specific technical requirements for each individual device. It wasn't one size fits all.
Okay, tailored to the device. Now, here's where it gets into fundamental safety. I saw a point about making sure maximum levels of microwave radiation at workplaces weren't exceeded.
Yes, absolutely paramount. The standard explicitly requires all measurements to follow strict safety regulations.
Which includes?
Everything from general electrical safety, rules for handling X-ray sources or radioactive substances if they were relevant,
Right.
and crucially, ensuring microwave radiation levels where people were working stayed below the established safety norms.
It really underscores that this isn't just about abstract numbers, it's about protecting the engineers and technicians.
Exactly. They're working with powerful, invisible energies. Safety first.
Really brings home the real-world implications, doesn't it? Okay, so people are safe. Let's dive into the core challenge. How do you actually measure these invisible forces, starting with raw power? How do you precisely measure the output when it could be tiny microwatts or massive kilowatts? That sounds tough.
It is indeed. The standard lays out three main methods for output power, each designed for different power levels and applications.
Okay, method one, I heard it involves water.
That's the one, the direct calorimetric method. It's mainly for higher powers from zero point 0.1 kilowatts up to a massive 103 kilowatts.
100 kilowatts.
Yeah.
Wow.
And the ingenuity is kind of in its simplicity. The concept is basic physics.
Yeah.
Measure electrical power by measuring the heat generated. The microwave energy gets absorbed by a load in the device, and that heats up a calorimetric liquid.
So you're literally using the temperature change of a liquid, like water, to figure out the power. And the document mentions drinking water for real.
For real. For open systems, yes, readily available drinking water. For closed systems, they specify distilled water.
That seems almost low-tech for this field.
But it's robust. Water has a very well understood specific heat capacity. It's a reliable way to measure absorbed energy. Simple, maybe, but a direct application of physics.
And the accuracy.
This method aimed for 10%.
Okay, plus or minus 10%. Surprisingly elegant. What's method number two?
That's the calorimetric substitution method. It's for a slightly lower range, 0.02 up to 10 kilowatts.
Still pretty hefty power levels.
Oh, yeah. This one refines the calorimetric idea. Instead of just measuring the heat from the microwave energy, you substitute that microwave energy with a known, calibrated amount of AC or DC electrical power, usually from a heater placed right near the load.
Ah, okay. So you generate the same thermal effect, but with a power source you know precisely.
Exactly. You swap the unknown microwave power for a known electrical power that produces the same heat.
That sounds like it would be more accurate.
It is. By substituting with a calibrated source, you isolate variables better. This method boasts higher precision, typically 7%.
7%. Better. It's like using a known weight to measure an unknown one on a scale.
Precisely. Using a known standard to measure an unknown. Classic metrology.
Okay, and then there's an indirect method for a really wide range, from microwatts up to 10 kilowatts.
That's right. This sounds like it would need some specialized gear.
You got it. For these much broader power levels, this method uses specialized converters.
Converters. Like what? Things like bolometric, ponderomotive, thermistor, thermoelectric, or electronic types.
Okay, break those down a little. Bolometric?
A bolometer changes its electrical resistance based on the heat from the absorbed microwave energy. A thermistor is similar. Resistance changes with temperature.
Right. And ponderomotive, that sounds different.
It is. Ponderomotive converters use the actual physical force, the pressure, exerted by the microwave fields.
Wow. Measuring the push of the waves?
Essentially, yeah. And thermoelectric types generate a voltage based on temperature differences caused by the microwaves.
So all these converters turn the microwave energy into some kind of electrical signal you can measure easily.
Exactly. That's the core idea. Now, the precision for this indirect method, it varies with frequency.
How so?
It's about 15% for the range from 0.03 up to 37.5 gigahertz.
15%. Okay.
But then it gets a bit less precise, 20% for the higher frequencies, above 37.5 gigahertz, all the way up to that 178.6 gigahertz limit.
So accuracy drops off a bit at the really high frequencies.
Yeah, that shift in precision shows how much harder it gets to accurately measure these incredibly fast, short wavelengths. The physics just gets trickier.
Fascinating. The act of measurement itself becomes more challenging as you push the boundaries. So we've covered raw power, but what about amplification? How much does a device actually boost a signal? That's obviously fundamental for amplifiers.
Absolute critical for characterizing any active microwave device. The standard details three main ways to measure power gain.
Okay, let's hear about the first one.
That's the compensation method. It's mostly used for devices with lower output power, say up to 1 watt.
Compensation. How does that work?
The concept is quite neat. You measure the gain by essentially canceling out the device's amplification with a precise, known amount of signal attenuation at the output.
So like balancing a scale again.
Kind of, yeah. Imagine you put a signal in, the device boosts it. Then you use a calibrated attenuator, like a precise volume knob, to turn the output signal back down until it matches the original input level.
Ah, I get it. The amount you had to turn it down is the gain the device provided. Clever.
Exactly. It's a very smart way to get an accurate reading. This method can achieve really good precision. 0.6 dBs for gains up to 50 dBs if you're using a smoothly adjustable attenuator.
0.6 dB. That's a tiny margin.
It is. Very precise. If you use fixed attenuators, it's slightly less, 0.8 dB. But still, very good for ensuring signal fidelity.
Okay, that's the compensation method. What's
Yeah.
the most sort of straightforward approach.
That would be the direct method. As long as your input power is reasonably strong, say 10 microwatts or more,
Yeah.
you just measure the output power, measure the input power, and calculate the ratio. Output divided by input.
Simple as that. Direct comparison. Makes sense.
Yep.
Straightforward.
But then there's a third one for low noise devices. That sounds trickier, dealing with noise.
Right, the noise signal method. This one is really ingenious, especially for super sensitive, low noise devices. Think things used in deep space communications or very precise radar.
Okay, where the signal itself might be incredibly weak.
Exactly. So this method involves comparing the noise power at the device's output under two conditions. First, with a calibrated noise generator at the input turned off, and then with it turned on.
So you're adding a known amount of noise and seeing how much the output noise changes. Precisely. Because these devices are so sensitive, even small changes in noise, either their own internal noise or the added calibrated noise, can tell you a lot about their amplification characteristics. You don't need a big, clean signal.
Wow. You're using the background hiss itself to understand the amplifier. That is clever.
It really is. And it's highly precise, too. The accuracy ranges from 0.2 dRains for lower gains, less than 20 dRains.
0.2.
Yeah, up to 0.4 dBr for higher gains, between 40 and 60 dBr. This shows just how vital accuracy becomes when you're dealing with really faint signals where keeping a good signal-to-noise ratio is everything.
Incredible precision for something so subtle.
Yeah, getting covered. Now, connections. How components talk to each other is vital, right? Let's talk VSWR, voltage standing wave ratio. What is that?
VSWR, yep. Fundamental parameter in any microwave system. Think of it like impedance matching.
Okay.
If your microwave signal is flowing on a transmission line, like power through a pipe, and it hits a connection to another component, say an antenna or another amplifier.
Yeah. If the impedance, the electrical characteristics don't match perfectly at that junction, some of the signal power gets reflected back, like waves hitting a wall and bouncing off.
Ah, reflections. That sounds bad.
It usually is.
Yeah.
VSWR measures the ratio of the maximum signal voltage to the minimum signal voltage along that line, which tells you how bad those reflections are. A low VSWR, ideally 1.1, means a perfect match. Smooth flow, efficient power transfer.
And the high VSWR.
Means lots of power is bouncing back. That causes inefficiency, signal loss, maybe even damage to the components generating the power.
Got it. So it's crucial for system performance. How many ways did the standard have for measuring this?
Given how important it is, the standard actually outlines 5 different methods for measuring VSWR.
5. Why so many?
To cover different situations. Measuring it when the device isn't even powered on, measuring it under various operating modes, different power levels. It reflects the need to ensure a good match under all sorts of conditions.
Right. Makes sense. And the precision for VSWR? Is that consistent?
No, it actually varies quite a bit, depending on the method and the actual VSWR value being measured.
Yeah.
Precision can range from 15% for a pretty good match, like VSWR less than 2,
Okay.
up to 30% for a worse match, say VSWR between 2 and 5.
30%. That seems like a big uncertainty.
It shows that accurately measuring reflections, especially when they're significant, is actually quite challenging. Even assessing basic connection quality needs advanced techniques.
It's not just plugging things together, it's about that perfect electrical handshake.
Exactly, a perfectly matched connection. And beyond that single-point measurement, the standard also goes deep into stability and consistency.
Right, because a device might work perfectly for a moment, but what about over time? Or if the temperature changes?
Crucial factors. They measure several things here. First,
Yeah.
gain non-uniformity.
Meaning?
How much the device's amplification varies across its operating frequency range.
Yeah.
You ideally want it to be flat, right? Amplify all frequencies within its band equally.
Yeah, otherwise the signal gets distorted. Like a bad equalizer.
Precisely. This is measured using methods similar to the gain measurements compensation or direct comparison, aiming for 10% precision.
Okay, ensuring a flat response. What else?
Then there's gain instability over time. How stable is that amplification over, say, a few hours?
Right. Does it drift?
Exactly. This is measured by compensating for any changes with an attenuator, tracking the drift. They aimed for 25% precision here, essential for anything needing long-term consistency, like comms links.
You don't want your satellite signal fading randomly.
Hmm.
Makes sense. And temperature, huge factor, I imagine.
Oh, absolutely. The temperature coefficient of frequency, this is fundamental.
What does this measure?
How much the device's main operating frequency shifts when the temperature changes. Either the device heating itself up during operation or the surrounding environment changing.
Ah, so the frequency itself can drift with temperature.
It can. And for things like precise radar or GPS, even tiny frequency shifts are a disaster. This measurement had a precision target of 20%.
So temperature affects not just physical stress, but core electrical behavior like frequency. Wow, lots to keep stable.
Indeed.
Okay, we've done power, gain, connections, stability. Now let's get into the really fine details. Phase and linearity. This sounds like the subtle stuff, signal integrity.
It really is. These measurements are vital for understanding how signals are shaped, modulated, and sent without distortion or losing information.
So what's electronic phase shift?
Okay, electronic phase shift measures how the phase difference between the input and output signal changes when you vary the electrical conditions within the device, like the current or voltage to its electrodes.
Why measure that?
It's critical for devices designed to manipulate phase. Think phase shifters used to steer radar beams electronically, or modulators in complex communication systems. You need to know exactly how changing the voltage changes the phase.
So you're checking how well you can control the signal's timing intentionally.
Exactly. Then, slightly different, there's amplitude phase conversion, often called AM to PM conversion.
AM to PM, what's that measuring?
This measures how much the phase difference between input and output changes when the input power level itself changes.
So does the timing shift just because the signal gets louder or softer?
Precisely. Ideally, it shouldn't.
Right.
If it does, it's a key indicator of nonlinear behavior. It causes distortion.
Like an audio amp changing tone with volume. Got it. A measure of fidelity.
Yes, it reveals how linearly the device handles amplitude changes without messing up the phase. Then there's nonlinearity of phase frequency characteristic.
Okay, another nonlinearity one.
This looks at how much the phase response deviates from a perfectly straight line as you sweep the frequency across the device's operating band.
So as frequency changes, the phase shift should ideally change linearly, proportionally.
Yes, if the line wobbles, it means different frequencies are experiencing slightly different delays. This can mess up complex signals where timing across frequencies is critical.
Like trying to keep a marching band in sync if different instruments have random delays. Okay.
Finally, the upper limit of amplitude characteristic linearity. This sounds important.
It is. It defines the input or sometimes output power level where the device's gain starts to change by a specific amount, usually dropping by 1 dB. It tells you the point where the device stops behaving linearly. So basically, the power level where it starts to distort the signal because it's being pushed too hard.
In essence, yes.
Oh.
Beyond this point, it'll start compressing the signal, generating unwanted harmonics, distorting it. The precision here was aimed at 15–20%.
Absolutely crucial for designing systems, especially comms, where you need to keep signals clean and avoid distortion.
Exactly. You need to know the limits of linear operation.
Wow. Okay, we have really journeyed through an intricate world here, guided by this old Soviet standard GOST 2271.1-91, from measuring raw power with literally water to detecting these tiny phase shifts and subtle distortions. The precision and, honestly, the ingenuity involved are quite remarkable.
It really does highlight the foundational work, often completely unseen, that makes so much of our modern technology possible. Every calibration, every check in documents like these, it all adds up.
And for you, the listener, this isn't just about some old technical document, right?
Not at all.
It's about appreciating the hidden complexity, that relentless hunt for precision that underpins almost every advanced bit of tech you use. Your Wi-Fi router, satellite TV, GPS.
Every perfectly tuned signal, every reliable connection, it depends on these fundamental measurements, these often unsung measurement heroes, you could say.
Think about streaming HD video without buffering, or getting pinpoint GPS directions, or just a clear mobile call.
None of that happens by accident.
No.
It relies on engineers having rigorously defined, measured, and controlled these invisible microwave parameters, making sure they behave exactly as needed.
So maybe the next time you marvel at some high-speed data transfer or a crystal clear image from space, just take a second and consider this. What other invisible forces are being meticulously measured, precisely controlled, and managed in the background, shaping our modern world in ways we probably rarely even appreciate?